minus a 1. So I arbitrarily just made up these numbers to try out a whole lot of different subtractions. And now we have a point where the b number is larger than the a number, and we end up with the 2's complement showing a negative number because the sign bit is going to be high. If you have an FC, the most significant bit is a high, which means it's a negative number. So these are negative numbers. Anytime the most significant bit is a high. And then let's see, here's not a negative number. We've got the number 10 minus e, that's 2. And now we're going back to the addition again. So take a look at these results and make sure they make sense to you. Students often ask, how do you get those arbitrary values into the A string, B string in figure 7-32? Well, selecting arbitrary values in the vector waveform file was covered back in example 6-9, back around figure 619 and 620. But let me go through this again briefly for you right now, just to refresh your memory. Basically, what you do is you highlight the area that you want to change. Of course, first of all, you had to build a vector waveform file. That was described back in chapter 4, and you'll have to go back there and read about that if you wanted to refresh your memory. And let's say I wanted this low. You just go over here and select low, and it turns out low. Select this area. Maybe we want this many to be high, and so on. And we'll just finish this off at 16 microseconds. I'll make that a low. Then in the A string area, if you right-click and say value and select count value, and we'll have the radix set at hexadecimal, which it is, starting at 0, ending at 3f, increment by 1, binary type, and make sure the timing is set up right, going from 0 to 16 microseconds. The default on this may be in a nanosecond, so make sure you check this out. Count every 10 nano, okay, so that's wrong, so let's count every 1 microsecond, okay, and there it is. Now we have this count value, and let me bring this back over so we can see all of it, okay, and you can arbitrarily just change numbers. Let's take this number 2 and change it. If you double-click on it, and if you right-click, insert, or I'm sorry, say value, arbitrary value, you can just type in the number you want. Let's put in a 44. So we've got 44 there, and so on. So you can go down and change these numbers any way you like, and in the B string you do that the same way. And then when you run the simulation, you'll get to see the output result. Let me do that for you. I'll pull up the one that was set up in the textbook. And here it is. These are the numbers that are right out of figure 7-32, and I'll run the simulation. And we'll see that the output worked out. It's a little crowded here. I don't know if I can make a little more room. So you can read these, and here it is, just like we discussed from the textbook. Okay, next, let's take a look at the design of a BCD correction adder using if-then-else in a VHDL program. So what we're going to do in example 727 is to write a VHDL program to duplicate the BCD adder that we looked at back in figure 725. We'll assume that the 4-bit inputs on A and B will always be valid positive BCD numbers. When the two BCD numbers are added together, we'll be using an if-then-else statement to determine if the sum is greater than 9. If so, then that sum must be corrected by adding 6. So in figure 733, the first thing you'll notice is that we have this IEEE standard logic unsigned as a declare. And the reason we have to do that is when you're working with BCD numbers, the MS bit may be a 1 just because it's a valid BCD number. We don't want that to be treated like a negative number. So we use unsigned. That'll treat all numbers as positives. So we have the A string, B string set up as a 8-bit vector, and the BCD result set up as an 8-bit vector. And then we have an intermediate internal interconnect signal called the binary result, just like we had to do back earlier in the chapter with that intermediate step. This is going to receive the sum of the A string plus the B string. And then in the process, the sensitivity list says, hey, if there's ever a change in either the A string or B string, begin this process. And then down in this process, we check, is the binary result that we got from up above, right, from here, from the addition, if the binary result is greater than 9, then the BCD result has to have 6 added to it. Otherwise, it's just equal to whatever you came up with in the first place. So here's how we do the correction. Now, the block symbol file over on the right shows us that we have an 8-bit vector coming in for the A string and the B string, and an 8-bit BCD result coming out. So let's look at a simulation of this. In this simulation, I've got the radix set up as binary, so we can see the BCD numbers. Like, for example, here we have a 0, 8. Here we have a 0, 7, and so on. So the first number is 8 plus 1, and we got 9 for an answer, 0, 9 for an answer. Notice I'm just using the LF digits in all these examples. Here I have 0, 7 plus 0, 8. 7 plus 8 is a 15. Now, we would have gotten the wrong answer. We would have seen an F down here, but the BCD correction took care of that, added 6, and so we ended up with the number 5 here and the number 1 here, which is 15, which is the correct answer. So I'll leave it up to you to go down through the rest of these additions and make sure that they're all correct. And then at the end of the chapter, there'll be a couple homework problems for you to make some modifications to the circuit and test it out on your own. So this concludes the second part to section 711. Next, in the final part would be to build a adder subtractor using a LPM. So stay tuned for that. Hi, this is Professor Clyde. So part 3 of this section 711, I'm going to talk about how to build an LPM adder subtractor. So this is illustrated in example 7-28, and what I'm saying here is rather than reinvent the wheel for each digital design, Quartus 2 software provides a library of pre-designed complex logic functions commonly used in digital systems. It's called the library of parameterized modules, and it's found in the mega functions arithmetic subdirectory. So I'm going to fire up Quartus and show you how to insert these LPM symbols and how to modify them. So first you start a new, or build a new file, so it's block diagram schematic file, okay. And then in the area, you right-click and say Insert Symbol. And for the symbol name, LPM underscore add underscore subtract. Oops, I misspelled that, ADD. And it finds it. Make sure that the Launch Mega Wizard plugin is checked, and say OK. We'll choose VHDL for our output file type. Next. Cyclone 2 is already checked, and we'll choose 8 bits as the width. Let's create an add subtract input port to allow me to do both. 1 adds, 0 subtracts. Next. We'll say both values will vary. Let's do unsigned arithmetic. Next. And as per our previous designs, let's check create a carry borrow input and a carry borrow output. Next. We'll select no for pipeline. Next, and finish. Yes. Then we'll drop this here, and this is our LPM. Now we just have to hook up the inputs and outputs to it. So we'll have scalar inputs, single node lines, which will be the add subtract. It's just going to be a high or low. The carry in is going to be just a high or low. Data A and data B are going to be 8-bit vectors, and the result will be an input vector. And the cout will be a single scalar node. So let me wire all this up and come back and I'll show you the result. So here is the LPM totally wired up, and we have the add subtract, like I said, single nodes, CN. Here's our 7.0 for our vector A input string. Here's our B input string, and here's our output result, which is 7.0, and with a possible carry out. So the only other thing we need to do is to run a simulation. And before we do that, let me just point out that these are the bus names, and the bus line, you can see it's a little bit thicker than the node lines. And this is the LPM mega functions inside the dotted line. So now let's look at that simulation. So I built these waveforms using a procedure similar to what I just showed you in the last podcast, and I set up the CN as there's no carry in, and then I'm going to have one for a couple periods, and then none, and then a couple later I'll have some carry in, just so we can exercise all the features of this LPM. And we'll start out by doing an addition, and we'll do subtraction later on. And for the A string, I have a 0,2, for the B string, a 3A, and when you add these two together, sure enough, you'll get 3C, which is the correct answer. And of course, this is an hexadecimal radix. And then we have 0,1 with an FF. That's going to cause a carry out because you'll end up FF plus 1 is a 0,0 with a carry out. And then 3 plus 2 without a carry, 3 plus 2 is a 5. And then with the carry in, 3 plus 2 is a 6. Makes sense? And then 6 plus 4 would have been an A, but we have a carry in, so we get a B. And then we get into subtraction mode, so we'll have 7 minus 5. 7 minus 5 is 1 with a carry out. However, this is not the correct answer because whenever you're doing subtractions, the CN has to be held high. We'll get the correct answer when we have the CN high. For example, 25 minus 3 is 22. That's correct. 25 minus 26 is an FF. That's correct. And the reason is that LPM defines CN by saying CN input is added to the result during addition, and its complement is subtracted from the result during subtraction. So when you go back into the definitions of the LPM, you'll see that description. So really, when I ran the simulation, I should have taken the CN and made it high during the entire time that the subtraction was being taken place. The other issue is remember, you always get a carry out of the MS bit of any valid subtraction, and we just ignore that carry out. And we covered that earlier in this chapter. So that completes this. I hope you got to see the power of the LPM. We'll be using these quite a lot throughout the rest of the textbook. And so that's it for Chapter 7. Be sure that you try the FPGA problems at the end of the chapter to solidify your knowledge of all of these aspects. Hi, I'm Bill Clyde. The material that I'll be covering in this podcast is out of my Digital Electronics 9th edition textbook. I hope you find it useful. Hi, this is Professor Clyde. In Chapter 7, I'm going to cover arithmetic operations and circuits. As you may know, it's very important to be able to perform arithmetic operations in any kind of digital system. And in this chapter, I'll show you how to perform these operations. First of all, the chapter pretty much can be divided into two basic areas. First of all, I want to talk about the actual operation of arithmetic using binary arithmetic, and then we'll look at the 2's complement, hex arithmetic, and BCD arithmetic, and we'll go through the steps on paper. And then in the section 6 to 11, we'll actually build the actual circuits using MSI, integrated circuits, and FPGAs later on. And we'll see how simple it is to actually build adders and subtractors and multipliers and dividers and so on. So before we actually build the electronic circuits, let's take a look at the operations for addition, subtraction, multiplication, and division. First of all, in addition, when you're in the least significant column, you will have, if we're just adding two numbers, you could be adding 0 plus 0 in that column, or 0 plus 1, a 1 plus 0, or 1 plus 1. And if 0 plus 0, of course, is 0 for the answer, and there's no carry. 0 plus 1, you'll have 1 with no carry, and 1 plus 0, 1 with no carry. However, if you have 1 plus 1, you can't write the number 2, so you have to write down 0 and realize that there's a carry out. So in general form, this is the least significant column. Notice A sub 0, B sub 0. So when you add these two, you'll get, this is the summation symbol, you'll get the sum plus a carry out. So in truth table form, same thing I just got through saying. 0 plus 0, 0 is in the sum bit, and no carry out. And then finally down at the bottom, 1 plus 1, the sum is 0, but again, you can't write the number 2. You're only allowed the digits 0 or 1. So that'll be 0, but we have to have a carry into the next column. Now, in the next column, as I show in figure 7-1, the addition in the more significant columns require including the carry in from the least significant column. So now, we added A0, B0, and got the sum with carry. If there's a carry, that carry goes up and over as C in the next column. Now you got three things to add. So that's what the truth table is going to look like. We're going to call this a full adder. We're going to have 3 bits to look at. 0 plus 0 plus 0 is no sum, no carry. Here we go with a 1, we'd have a sum with no carry. And let's get down into here. 0 plus 1 plus 1 is 0 with a carry. And anytime you have 2 or more, here's another 1, 0, 1, 0 with a carry, 0 with a carry. But the last one's kind of interesting. 1 plus 1 would have been 0 with a carry, but when you throw 1 more in there, you'll get 1 with a carry. Think about it. This one here, 1 plus 1 plus 0, 0 with a carry. So if you throw 1 more in there, you'll have to account for that, so now it's 1 with a carry. And so now that we've built this truth table, let's take a look at some actual examples of addition. So in example 7-1, I'm going to perform several decimal additions and then convert the original decimal number over to binary and add them again. So here are the series of additions I'm going to do. Let's just start with part C, which is the number 18 plus 2. Now we know that 18 plus 2 is 20. Now let's do it in binary. Now the number 18 would be made up of a 16 and a 2. That's where these ones came from, right? 16 and a 2 plus the number 2. And I've got these leading zeros in here. And then you would go down through and add bit by bit. In LS column, 0 plus 0 is a 0. 1 plus 1 in the next column is 0 with a carry. Carry comes around. And in this column, we'd have 1 plus 0 is a 1. And we come around, and we have 0 plus 0 is a 0. And then finally, in this column, we have 1 plus 0 is a 1, and we're done. And when you check out this sum, this bit is worth a 16. This is worth a 4. That's 20, and it checks out. Let's try 147 plus 77. 147 is made up of the 128 bit, the 16 bit, the 2 bit, and the 1 bit. Check that out yourself off to the side. The number 75 is made up of the 64, the 8, the 2, and the 1. And now when we add these up, of course, when you add it up in binary or in decimal, you come up with the number 222. And if we did it in binary, 1 plus 1 is 0 with a carry. The carry comes over. 1 plus 1 plus 1 is 1 with another carry. The carry comes over. 1 plus 0 is 1, no carry. 0 plus 1 is 1.